Hello everybody. Last time we discussed about the postulates of special relativity and devised a way of looking at space-time events and trajectories of particles in space-time. Essentially, we learned how to do the space-time diagram, how to do measurement first, and use that concept to do the space-time diagram. Today onwards, we will try to see the consequence of the postulates. And the first consequence will come through a thought experiment. Now, this is something may bother you. How can experiment can be done through just thinking? It is just that you simulate a situation in your head and try to see what is the outcome, maintaining all the consequences and all the rules of the game. Okay, so you'll use the rules of special relativity to see what outcomes do we get out of a thought experiment. And this thought experiment, what I have is a train, just like the train I had in the first day example. So I have one person standing at the middle of the train. I call this person O, this position O. The end, two walls at either end have mirrors. So as you can imagine, I like to bounce light back and forth from those. So this is one requirement I have. The other thing, so this, like, I'm listing the apparatus: a double-headed torch. So, like, I have a torchlight. Usually the torchlight looks like this, right? The light comes out of this way, but now it's a double-headed torchlight, so the light can come out from the either way. If I push a button here, so light comes out from the either way. So these are the two things that I have obviously two sets of observers, but that is, you can imagine that I have to define reference frame and do measurements. But other than that, this is what I have. And let us first see what happens. Now, what our job is to try to figure out a same experiment as seen from two different reference frames. So one reference frame consists of one set of observers, another reference frame, another set of observers, one reference frame. So let me draw the train now. It's the best I can draw a train, two wheels. So these set of observers are at the train. So this is not a wheel, this is that O, and then the ends I call A and B. Okay, so there is a set of observers on the train. This is the person who is throwing the light beam in either side. And remember, I have a mirror here and I have a mirror here. Okay, there the events that will measure at the position of the two mirrors and the position of this observer, of this person, so that person can itself be an observer, and A and B are the, at the position A and B, there we need two other observers. This distance is L, and this distance is also L, so he's standing at the middle of the train. Okay, so let us start drawing. Let's start using our tool, which is the space-time tool of space-time diagram, and start drawing trajectories. So this is X, and let me, okay, so let's first draw in this reference frame. This is a reference frame where all these observers are on the train. So if the train moves, they doesn't know they are on the train. They move with the train. So they always, obviously all the observers stay stationary with respect to themselves. So all these observers, so their initial positions are, say, A, O, this distance is L, and B, and this distance is again L. So they stay where they are, so they always stay rest. And we know how to draw the world line of such observers. They are lines parallel to the y-axis. Right? So these are the world lines of the observers at O, A, and B. Now, what is done is, at t equals to t0, the observer at O, who has the torch, switches on the light. So the light goes, it hits the observer at B, comes back to O, hits the observer at A, comes back to O. Okay. We want to draw the world line of light. Now the light starts at here, because that's the position of the observer at O at t equals to 0. And remember that light goes always in 45-degree angles, because the speed of the light is c, and remember tan theta is v by c, so c by c becomes 1, so theta is 45-degree. So the light that comes out from here goes at 45-degree angle. So if I draw which is going towards B, so I have to draw it at 45-degree angle. Imagine that is 45-degree. So that is the trajectory of the light. I draw it with wiggly line. And then what happens at B is it gets reflected off from there. It will reach there. Okay. So this is an event that happens here. So and that happens at a time, let's call that time TB. So the coordinate of this is CTB, comma, XB. XB is the position at B. Similarly, this is the light that goes towards A. It hits here in the mirror. That happens at a time, say, CTA, and it's obviously at XA. So XA is written on the top of the paper of the observer at A, and he writes down the time CTA when he sees the light reaching him. And then the light goes back. Okay. Now you see, speed of light is same in all reference frame. It doesn't matter whether the cart is moving or not. That is our second postulate. What is it telling you? It's telling you that they has to reach back at the same point, because both of the sides they're going a distance L, so they has to reach back at the same point. If you look at the triangle made by, so let's call these positions P and this position Q. So if I look at the triangle PBO and the triangle QAO, These angles are all 45 degrees by definition. These angles are 90 degrees. So these triangles are just the mirror images of one another, right? So one, if you invert, you will get the other triangle, which also essentially means, so if I look at these triangles, from that I can come to conclusion now that TA has to be equals TB, right? I should have written this down below. Let me do that. Bring it here. Okay. See, TA has to be TB. So what does it mean? It means that the two ends of the at the two ends of the cart at A and B, the light has reached at the same time. So this is a single time here at which the light has reached two ends. Okay, so we can say that TA, or let's say not TA is the time itself, the events Q and P are simultaneous, means that they happen at the same time. Okay, we always talk about this simultaneous. Oh, it's just these two are happening simultaneously. So this is here in the space-time diagram. We see that the light is hitting A and B, who are completely spatially separated two different points. The events are measured by two different observers. But when they come back to their cafe to measure, to compare their notes, they will see that they have written down the exact same time in their different clocks. So TA in this case is TB. Remember that they're talking about two different events, and these two different events are happening at the same time for them. Very nice. Let us now analyze the same situation from a different perspective, from another inertial reference frame. Okay, so I make a divide here because here in the other side we'll discuss a different inertial reference frame. This is a reference frame where this cart is moving with a velocity v in the positive x direction. Everything else, so I label them as OA, B again. And obviously the same experiment is being done. What is happening physically is not different. It's just looked up by the observers who are stationary in the track. So now we can see that again different observers will measure different things, but it's now measured by these observers. Okay. So let me remove the person from inside because you may confuse that there is another observer inside the train, but there is no observer here. But obviously somebody is throwing the light, and I mean it's the same thing is happening. It's not two different things that we are considering. It's just we are looking at the same phenomena from now a different reference frame. Okay, let's see what our space-time diagram tells us. So now because these are two different reference frames, let's give them names. So let's call this S and let's call this S prime. This prime stands for a different frame. So all the times we will call, so let's not call this T prime here because that will confuse us tremendously. So let me call this T. Let's call this T. Say T0 if you wish. Okay, so this is CT prime this way and X prime this way. At T equals to 0, T prime was also 0, and then the observers in the two different reference frames will coincide. They will be at the same point at the same time. So these are the initial positions at t equals to 0. But now what happens? Now we are looking at events happening at three different places, A, O, and B. And if I ask the question, what is the velocity of A? We will say, well, it's part of the train. The train is moving with velocity v. It's supposed to be a rigid body type of object. So it will have a velocity v. So as for O or B, all of them will have a velocity v along the positive x direction. So how will their world lines look now? Remember, something moving with a velocity v along positive x has a slant in their world line towards positive x. So these world lines now look like this. So A, O, and B will have these world lines. And then we'll play the same game where from here I will send light rays. But remember, light moves at the speed of light always in all reference frames, second postulate, which necessarily means it will still move at 45 degrees. So it will have these wiggly lines at 45 degrees. It will reach somewhere here. So that's the event P. It's the same event P over here. Obviously, it can have different coordinates because I am in different reference frame now. The position is different as measured by these observers. And the time is also measured by those observers. So in their paper, they're writing down one side. What about the other side? Well, it will go on 45 degree and it will reach somewhere here. So that will be the event Q. So this is like when the light reaches the mirror at A. So this I will call C T A prime X A prime. Okay. Now, because of the slant in the line, it is quite clear that this and this are not happening at the same time. So T A prime is not equals T B prime. See, mind you, it doesn't mean that Q and P are different events. They are exactly the same events as in here. This Q is the exact same event as in here. This P is the exact same event as in here. But when this set of observers in the S frame come and compare, they see that the time for the event P and the event Q they recorded are same. So they call these two events simultaneous. Whereas when these observers measure the time from T and P and Q, they compare, they say that the events Q and P are not simultaneous. Well, that's something interesting, right? Two events, you and your friend, for a set of observer may take birth at the same time. For another set of observer, one of you can be elder than the other. This is what it means. In this case, Q happens earlier, P happens later in this reference frame. So Q is elder than P. And I request you to draw the space-time diagram when the cart is moving in the other way, and you will see that in that case Q will happen first, P will happen first and then Q will happen. So this essentially is telling you that events, simultaneity of the events is a relative context, is a relative concept for all reference frames, two events may or may not be simultaneous. Okay, so this also tells you that the time is a relative concept. And now if you think about the Galilean transformation, where we said the time measured in one frame is exactly the same as the time measured in other frame, that cannot be true anymore, because in that case the simultaneity would have also held. So we need to now change our transformation rules as well as a consequence of the postulates of special relativity. And that's what we will learn now. So let me first write down for you the Galilean transformation. Remember, we said that the t does not change, so this is what we should change now. And then this was x minus vt, y prime was same as y, and z prime was same as z. So in this case, the relative motion or relative velocity of the two frames is v along x direction. Okay, positive or negative will change this sign over x minus vt. It can become x plus vt, but that is what this transformation law is for. From the postulates of relativity, we can actually derive a new transformation laws. The derivation is out of the context of this course, but I will write down the transformation laws here. It's called Lorenz transformation laws. And I will write it with the coordinate with ct prime, because as we have already discussed, and see that it also makes the equations look nicer in this case. So let me first write them down and then we will discuss. And I will define everything that I am writing new here. So hold for a moment. And again, this transformation law, this is true for both of them as well as there. Okay. And so let me define these two quantities I have written here. So beta is v by c, and gamma is something odd looking, 1 minus v square by c square. So I can write beta square also. So these are the Lorenz transformation rules. Okay, these can be derived from the two postulates that we have discussed, but we will not do the derivation. It is quite involved and it's not suitable to be done for this particular course. Now, if you look at a book, you may see that it's not written like ct prime equals ct minus beta x. Instead, it is written t prime equals t minus something. But that is just one way of writing. I have multiplied everything by c, just because then all of these have the same magnitude, same dimension of length. Also, if you look at these two expressions, they look similar. So when I write the transformation for t, I write ct here minus beta of x here. When I write for x, I write x here minus beta of ct here. Easy to remember. Okay, fine. So that's the Lorenz transformation. But one thing one need to make sure is that, well, Galilean transformations laws are well established transformation laws which you even use for practical purposes, and it was derived from experiments. So it's not that they're completely wrong. They may be correct at a certain approximation of the Lorentz transformation laws. And the approximation is when in our everyday life we never deal with a velocity which is anywhere close to the speed of the light. So if I consider v by c, which is also we called beta, is much less than 1, then let's see what happens. So v by c much less than 1. What happens to gamma? Well, beta is much less than 1, so I can forget beta with respect to 1, so gamma is just 1. And if I write the Galilean transformation, the Lorentz transformations now in this limit, you see the first equation becomes ct prime equals ct minus beta. Beta is very small, so it's like 0, so it not need to be written, times gamma. Gamma is 1, so ct prime is ct, which is nothing but t prime equals t. And x prime is x minus, well, beta is v by c, c cancels out, so x minus vt, and the entire thing times gamma, which is 1, so x prime is x minus vt. And obviously y prime will stay as y and z prime will stay as z. So these are the Galilean transformations. So in this approximation, or in this limit if you wish, the Lorenz transformation becomes the Galilean transformation, and that's what I expected to happen. Otherwise, obviously, all the experiments that Galileo did cannot be wrong. Okay, so in the rest of the discussions, first we will try to see what are the consequences of this Lorenz transformation. Okay, so let's go about the first consequence. So remember that we have considered two postulates of special relativity, and we have seen that time is a relative concept from a thought experiment which said that we have to change the Galilean transformation where time is not a relative concept. And so as we do that, we come to Lorenz transformation, and now we are discussing about the Lorenz transformation, the consequence of it. First thing is, let us consider two events. Okay, again I will, so though I have written down x, y and z for this, we will still again go back to our old description of one spatial, okay, one spatial coordinates. So two events we talk about. One is say EA given by CTA and XA. Other is EB given by CTB and XB. Now I will give you an exercise to calculate this. I define this first, SAB whole square. This is defined as CTA minus CTB square minus xa minus xb square. Okay. Now these two events, if I see from the other reference frame, so I can call them some prime, right? So just like we are talking the other reference frame, other inertial reference frame, we will always call them as prime. And I can also calculate this quantity, which is, see, again, remember that the events are A and B. The coordinate measurements are done from one reference frame here, another reference frame here. Okay. And for these two reference frames, each cases I am calculating this quantity. It has a name which I will tell you shortly. So this quantity is called interval. Okay. If you calculate, if you work this out, so how will I work this out? In place of CTA prime, I will write it Lorenz transformation, which is this beta x times gamma, so xa prime times gamma, minus CTB minus beta xb times gamma whole square, minus Lorenz transformation of xa, which is xa minus, so I'm just using these rules essentially, xa minus beta CTA times gamma minus xb minus beta CTB times gamma whole square. Okay. If you work it out, you will remarkably see that this comes out to be exactly what I have here. So this comes out to be SAB whole square. Okay. Or on the other hand, the interval as measured in the two reference frames are same. Interval remains, if something remains same, it doesn't change between reference frames, we call it invariant. So invariant is a word for remains same. So this essentially means remains same. Okay. Now that's a very important message. We will be using it shortly to show you something very, very interesting. So we realize that the interval remains same. If I do whatever Lorenz transformation, the interval doesn't change, right? So what did we do here? Again, I am considering two events, EA and EB, and so their coordinates are measured in two reference frames in two different ways, four sets of values. And then for each reference frame, I calculate this quantity, which I call the interval, and I see that the value of the interval comes out to be the exact same value for the two different reference frames. So interval is something that remains invariant, doesn't change if you change the reference frame. Okay, so now let us look at a few cases. Okay, so examples of intervals. Okay, so let's say that I have one event happening here. So this EA is here, and EB is here. Okay, so you immediately see this much is xb minus xa, and this much is ctb minus cta. And remember that the interval, or let me write it as SAB square. This is, what is the definition of this? CTB minus CTA square minus XB minus XA square. What do you think for this interval? Will it be positive, negative, or 0? Well, it's clear that it will be positive, right? Because I have lot more t than x. The vertical distance is much more than the horizontal distance, so this is greater than 0. What does it mean? SAB square is greater than 0. Now see, in this case, you see the time wins, right? There is more time compared to space. So this is called time-like interval. Because there is more time in this interval than space. And this is greater than 0 in one reference frame, and because the interval is constant across Lorenz transformation, it will be greater than 0 in all reference frames, right? Let's see what is the consequence of that. You see, these two events may lie in the trajectory of a person moving along this line with a constant velocity given by this angle. You know that angle is related to the velocity. Can I go to a reference frame? So let us ask a question. Can I go to a reference frame where tan theta is less than 1? What do I mean? If you remember, tan theta was c by v. Okay. V is the velocity of the object moving along this world line, right? In this reference frame. And in this reference frame, his theta is c by v. Okay. So let us imagine, so this is a question, I don't know whether this can be done, but I am asking, can I go to a reference frame where tan theta is less than 45 degree? So it will look something like this, two events. So say one event EA is here, the other event EB is here. Well, if it has to be true, you see what happens here. This is the, if I wish, delta t, the t difference, time difference in this reference frame, and this is the space difference in that reference frame, and here you will then have SAB square. The space difference is more than the time difference, space is more than time, this will be less than 0. So you are asking the question, tan theta has to be less than 1, tan theta is less than 1, that is how I draw this, some less than 1 trajectory, then SAB square has to be less than 0 in that reference frame. That is not possible. Why? Because SAB square is constant. SAB square doesn't change as we change the reference frame. It's an invariant quantity. So if I go to a different reference frame, let's call this primes as we are always doing. I cannot go to a reference frame when SAB square is less than 0. It is impossible. That we have already seen. So I cannot, particle moving along this trajectory, which is a velocity v, cannot go to a reference frame where tan theta is less than 1. How can I have tan theta less than 1? Tan theta less than 1 means tan theta less than 1 also implies v is greater than c, because that's how I will have tan theta less than 1. So tan theta less than 1 not possible also means v greater than c not possible. And there you come to the conclusion that no particle can have a velocity which is faster than the speed of light. I know that you have heard this before, but this is the logical development to this conclusion. And this comes from this time-like intervals. Okay, so these are time-like intervals. Let us talk about two other types of intervals, and I will not spend a lot of time in them. So let's say the example that was coming here, say there are two events happening. These two events are not part of trajectories, they're just two events. Like you are born in Varanasi, your friend is born in Jaipur, for example. So here, this is my delta x and this is my delta t, x ct. So here if I write SAB square, by definition it is CTB minus CTA square minus XB minus XA square. What do you see? What is greater now? The space difference is greater now. So this is less than 0. So in this case, SAB square is less than 0 for this type of the example of the interval that I have drawn here. And remember that one I said that SAB square is less than 0. This statement is independent of the reference frame. All reference frame it has to be true because SAB square is constant. So all reference frame space wins than time. So these are called space-like intervals. Okay. So there are a lot more interesting discussion that may happen with a space-like interval, but again, I will not go into those. A little bit more complicated and involved than what you pay for this particular course. There can be another one. You see, for the time-like intervals, the 2 points can be on the trajectory of a velocity in this theta, and theta is such that tan theta is greater than 1. So here, time-like intervals, tan theta is greater than 1. Space-like intervals, tan theta is less than 1. This angle is theta, right? So that is less than 1. What if tan theta equals 1? So let's try to draw such an interval. So say EA here and EB here. Okay, so this part is my delta x, this is my delta y, delta t, c delta t. So SAB square. So tan theta equals 1 essentially means that, let me write it down first. Okay. let us manipulate it a little bit. Let me take c square and tb minus ta square common, the first term. So I get 1 minus, you see, then I get xp minus xa by tb minus ta. That's like a velocity. So 1 minus v square by c square. And if xb, so the velocity is xp minus xa by tb minus ta, and if xb equals to xa and tb equals to xb minus xa and tb minus ta as such that these two arms are same, or say that if I put c back over here, these two are same, it will be v by c. This is equals to, my velocity is obviously then c, so this is 1, or my interval becomes 0. You see, what I am doing is I am considering 2 points on the trajectory of a light ray. Okay, so the velocity of along the trajectory is v, is equals to the speed of light, obviously. So c by c becomes 1, 1 minus 1 here is 0. So in this case, tan theta is 1 and sab square is 0. So these are called, you can call them null because null means 0, or this happens only on the trajectory of light, so they are called light-like intervals, which I don't have space to write. Okay, so this is what we'll discuss today. I will come to other consequences in the next lecture, but let me recapitulate what we have done today. We have discussed about the concept of simultaneity, where we looked at the same set of events from two different reference frames using our technique of space-time diagram. We saw that two events which are not happening at the same point. So remember, now we can say that q and p are space-like separated events because their spatial distance is more than the time distance. In this particular case, the spatial distance is 0. Sorry, time distance is 0. All its distance is spatial distance, right? So SPQ, so I can write now here S square PQ is less than 0. It's a space-like interval. It will remain 0 here, remain the same here, right? Because it's a constant. So for such space-like events happening at space-like intervals, we have seen that those events may seem simultaneous in one reference frame, not simultaneous in the other reference frame. So the concept of time becomes rather relative, and that required us to change the Galilean transformation. We said we could derive a new set of transformation rules, which we call the Lorenz transformation, from the two postulates only, and the derivation is out of the course scope of this course, but these are these transformation rules. And these transformation rules goes back to Galilean transformation when the velocity is much less than the velocity of light, which is all the velocities that we look in our everyday example. Then we discussed about one consequence, or discussed about intervals. The first consequence of the Lorenz transformation, we found that interval is a concept which is invariant or constant or remains same across Lorenz transformation. Different reference frame observers, when they compare their notes, if they calculate the interval out of it, they'll measure the same number. And that brought us to three different types of intervals, where the first we looked about the time-like interval, and we came to the conclusion that an object which is moving with velocity v, we cannot change the reference frame in any way such that in one reference frame it attains a velocity which is much greater than the speed of light, which is greater than the speed of light. That is impossible. And you see, that means that the Galilean velocity transformation rule will also change, because there I can just keep on adding velocities as I change reference frames, and eventually it will go greater than anything that you want. But that is not possible here, that we have seen here. And we also looked at two other types of intervals. In the next discussion, we will talk about three other consequences of special relativity and Lorenz transformation. Thank you for today.